Okay. Okay. Did you have any specific things about multivariable calculus you weren't sure on?
Just still the same thing, like how you do summary and the key points.
Yeah, that's the idea anyway. So this is the two-variable calculus bit of the notes. I'm just going to talk through it a little bit. You're used to one-variable calculus. What you're used to is that you have functions of one variable, and you have something like y equals f of x. And what you have is you've got an x down here and a y here, and it's some sort of curve. We're used to that because we did it in last semester, and you've spent a lot of time trying to get used to, well, if it's a quadratic equation, it should look like a certain thing, and if it's an e to the x, it'll look like a certain thing. And then we know how to do derivatives and all of that stuff. And the basic idea of your one variable calculus is that each number here on the x-axis goes into the function, and what the function does is it produces a new number, which is the y variable, which is there. Okay? That's the idea behind it. But what we can actually imagine is that this height here, that's the y that came out. That's the f of x. Okay, so we get our x, we put it into the formula, and it tells us the height. If I'd known I was going to talk about multivariable calculus, I would have brought the Plato. This actually would have been a lot more helpful, but I'll have to do without it, unfortunately. So with a function of two variables, let me go back before I talk about that. Sometimes with functions of one variable, there were issues where you had something like, you know, an asymptote, and it would do something like this near that spot, and it wasn't defined there. And so you'd have this spot where the function wasn't defined, and so you'd imagine that there was a domain which lived on your x-axis and told you the x's that you were allowed to use in your function. Okay, right. Functions of two variables have the same idea. I'm just going to take this because it's destroying it's getting hot in here. So functions of two variables are the same idea, but instead of only having one number to tell you what the height is, there are two numbers. Okay, instead of using an x to figure out what the y is, you use an x and a y to figure out what the z is. Okay, and so I need to draw a 3D picture like that, and then at every possible x and y on that plane there, okay, so that point has coordinates x, y, and then I use those coordinates to find a height, which is my f of x, y. And at every point, you figure out a height. So there's a height here, over at this point there's a height, at this point this has a height, and every point has its own height. Possibly a depth, it might go downwards if it's negative, okay? Okay, and the collection of all of those dots together form a surface, okay? So, maybe next year I'll do a proper one and I'll bring the Plato. So the collection of all of these points that end up at the top, which I'll just colour in a slightly different colour. Okay. Now you've got to imagine that there's some everywhere. They form this sort of wiggly, surfacey thing. That's the idea behind it. Because what happened back here is that each x produced its own height, and together all those dots that I made from those heights, together those dots formed the curve. That's what happened in our one variable calculus. So what I'm saying is that we get all the points here on this flat plane here, and we figure out how high we should go or how low we should go below from there, and draw a dot in space, and all of those dots together form a surface. That's the picture of two-variable calculus. Now that's the geometry of it. In most situations, like in economics and statistics, it's not geometry, because you're saying, well, I've got the number of chairs in my restaurant and the temperature in number of chairs in my coffee shop and the temperature today, and knowing those two bits of information, I try and predict what the number of customers is going to be today. And so you've got your X is your chairs and your Y is your temperature, and then your height is what your customers is. And it's just a formula that you put numbers in and it spits a number out. And it's not really geometry, it's just that thinking about it in terms of 3D geometry makes it easier. Because geometry, you can picture what's going on if you think about it carefully. And so what the two-variable calculus is about is trying to think about how that works in a careful sort of way. Right. So, I haven't added to this one picture. The domain here is just slices of the line. You might get bits of the line and there might be a couple of gaps in it. The domain is the bit of the x-axis you're allowed to use to produce these heights. Well now, because I'm not using an x-axis, I'm using an x and a y together, the domain might be some sort of wicked shape. And I'm only allowed to use combinations of x and y that are inside that shape. Okay, that's what the domain is there. Right. Works much better if I have a 3D picture. So, apologies to those who are watching on the video, you're not going to be able to see this. Unless, just a second. That's not good, is it? Aha! Right. Let's see if I can zoom in a bit. So, that's my x-axis. That's my x-axis there. And that's my y-axis there. And at every x, y, I can go up a bit and there'll be a point in space that goes with it. And at this x, y, I'll go up a bit, there'll be a point for that, there'll be a point for that. And together, all of those points might make a shape. And it might be a plane, or it might be something curved like this. Okay? That's the idea behind it. Every point down below will produce one of the points on this surface. Okay? That's the idea behind this multivariable calculus. And what we're really interested in is where is it its maximum and its minimum. That's what we used to be most interested in with ordinary calculus. We wanted to know here, what is that maximum point? Okay? So the idea behind it is that at that maximum point, it's sort of flat no matter which way you pick. I can put a tangent down on top of it in every direction. So what I need to do is find a way of figuring out the slope of those tangents. And when in ordinary calculus, go back to my document camera. In ordinary calculus, the slope of those tangents, right, that was given by the derivative. But now in 3D, there's tangents in every possible direction. So I need a different way of defining derivatives. So what I'm going to do is I'm going to define a derivative. So if I slice my surface down this way and parallel to the x-axis, I'll have a slope in that direction, and there'll be a slope in this direction too. And that's your d on dx, curly d on dx, and your curly d on dy. Right, now let's have a look at the notes and see if I can get to a bit that I'm interested in. Yeah. Right. Yikes. Okay. I'm going to skip the domain bit because I do actually have something about that on the internet. Just let me check that. Yeah, so the beginning of the two-variable calculus revision seminar that's already there has domains and ranges in it. Okay. Because I've got sort of 20 minutes until the next revision seminar group comes in, so I don't want to go over. So that's the picture. Now, in the Maths Learning Centre, there's some things made out of string there, and there's the one on the right that's in the school. There's one that's round. The other one is a surface like this. And if you ever want me to do this with Play-Doh in the Maths Learning Centre, please ask, because I will, because that's the best way of understanding this, at least that I have found. And you get a chance to play with Play-Doh, which makes your study much more fun. Okay, so what we're going to do, calculus is all about derivatives, and so we're going to talk about derivatives. Okay. So what you can do is that you can define a derivative in the x direction or in the y direction. So back to my I wonder if I have anything that's a nice shape. Just let me have a look under the No, it would have been nice. So I've got my surface, okay, which is whatever shape it might be. And I want to figure out a derivative in each direction. So what I'm going to do is I'm going to slice this surface down like this, so that it's parallel to the x-axis, okay? And when I slice my surface down like that, it'll slice this into a piece, and when I draw that, slice it down like that, it'll cut my surface and there'll be a curve there. Okay? You've got to use your imagination. I've got my surface here, it's squiggly, whatever it is, and then I slice it with a great big meat cleaver and I get that. Okay? And that shape is what I get when I slice my surface. And you'll see that that looks very much like what I would normally expect to see in an ordinary function. And so what I do is I redraw my x-axis on this piece of paper, and then I can just do the height as a function of just x. And I can figure out what this slope here is, just there, like that. And that slope is dz on dx. But if I had sliced it this way instead, I would have got a different curve, and I would have gotten a different slope, and it would have been dz on dy. That's the picture of what's going on. But the practicalities are you just have to know how to do it with the calculation. So slope of curve produced by slicing parallel to the y-axis. Okay? But in the end, the way that you create it in terms of the algebra is that you just pretend x is a constant and differentiate the y's. Okay? So differentiate pretending x is a constant. That's pretty much how you do it. So as an example, something like that, you can go, all right, well, dz on dx is, so we pretend x is a constant, right? Anything that doesn't involve a y is a constant. So e to the x is still constant, and so the derivative of a constant is 0. anything that's a constant multiplied will stay there when I differentiate, so that will still be there afterwards because it's being multiplied onto the y, so it will still be there. And the derivative of y squared is 2y. So that's 4xy. But on the other hand, if I did that's a y. If I did dz on dx, I would be pretending that y is the constant this time. So the derivative of e to the x is e to the x, and this time it's the y squared that's a constant. So now any constant that's multiplied will still be there afterwards. So the y squared will still be there because it's a constant multiplied on, and the derivative of 2x is 2. And that's partial derivatives. That's how you calculate them. You pretend that the other variable is a constant. And that curly D is reminding you that you are choosing the y out of multiple options, and all the other options have to be counted as constants. It takes a bit of getting used to, pretending that it's a constant. If you find that's tricky for you, what you need to do is you need to pick a number for x, a nice number that's not going to combine nicely with anything, like 7. 7's a good one, or 11. And what would it be if x was, say, 11? So this is what thing I do in my head. Like that. And I'll differentiate that with respect to y. And I'll go, oh, okay, cool. So dz on dy would be, that'd be 0, and I'd get that. And my 11 is really my x, so I'll just put the x, replace all the 11s with x's. So if you find it hard to remind yourself of what's going on there, you have to pretend it's a constant, so sometimes you can just make it a constant, just temporarily, while you're thinking about how to do it. So, yeah. Because that's the picture you're making, actually. You're saying, well, what if x is whatever x I'm interested in at the moment? Okay. Right, that's the first derivative. Now, back in one variable calculus, the first derivative told me when the turning points were. Okay? First derivative back here, when the first derivative was 0, it was these turning points. That's what happened when the derivative was 0. And so I'm going to do the same trick in 2 dimensions, but I need it to be a turning point in the y direction and in the x direction simultaneously. Because it can simultaneously, it can be a turning point one way but not the other, and I need it to be a turning point in both directions in order for it to be a maximum or a minimum. And so the idea is to find maximum or minimum, we need both dz on dx and dz on dy to be equal to 0 separately. They both need to be 0. So back when there was only one variable, we only needed one derivative to be 0, but now that there's 2 variables, we need them both to be 0 simultaneously in order for it to be a maximum or a minimum. Okay? So I should go back here and remind you that it is possible to write this notation in a different version. So, or if you like, it could be, sometimes they call this f with a little x, f with a little y. There's 2 different ways of writing it. So this is the D notation and this is the sub notation. Okay. Right. One more thing back here I would like to add to this. It's also the dz on dy is also the rate of change of z when y is changed, but when x is kept the same. But x is constant. Yeah. Okay. So there's 3 different ways of thinking about it. I just wanted to add that to the list. Okay. So Cool. Great. I will do a proper example in just a second. Back in one variable calculus, there was a way of telling whether your turning point, whether it was a bottom of a valley or whether it was the top of a hill, okay? And that was using the second derivative. So there's also a second derivative test in two-variable calculus, but it's much more complicated. To know if it's the maximum or minimum, or there's a third option in 3D, a saddle point, we need to do the second derivative. We need the second derivatives. So your second derivatives, again, there's a dx dx, and there's a dy dy, and there's a dx dy, and a dy dx. Okay? So there's 4 of them. Like that. And this can also be written as fxx, fyx, fyy. There's a small technical point there that this one is yx, but the matching one down here is the other way around. That's just a technicality of how these things were invented. But I have a diagram of how you do them. You start with your z, and you've got your x and your y. So if you differentiate with respect to x, you get dz on dx, or if you like, no, I'll do it with an f as well over the side. If you differentiate with respect to x again, you get dz on d squared z on dx dx. If you differentiate with y from that point, you'll get d squared z over dy dx. If you differentiate with respect to y, you'll get dz on dy. If you differentiate with respect to x, you'll get d squared z on dx dy. And these two should come out to the same answer. And if you differentiate with respect to y, you'll get d squared z on dy dy. But your other option is to do it with an f. If you differentiate with respect to x, you get fx. If you differentiate with respect to y, you get fy. If you do it with x again, it'll be fxx. If you do it with respect to y, it'll be fxy. If you do it with that, that'll be fyx. And that'll be fyy. So that's a really bad diagram over the side there, sorry. So if you want to find fxx, first, this is when you need fxx, first you need fx. If you want to find d squared z on dx dx, first you need dz on dx. So just as an example of how to find those second derivatives, I'll continue with the ones I had before. So I'm just copying out what I had before. That's a comma. Like that. So I know that dz on dx, d squared z on dx dx means I go d on dx first and then I do d on dx again. So d on dx means I'm ignoring the x. So I already had the dx and I'm doing another dx. So dx means I have to ignore the y and pretend it's a constant. So the derivative of e to the x is e to the x. The derivative of that is 0 because it doesn't involve any x's, it's all a constant. D squared z on dy dy. Well, this is d on dy, and I need another dy, which means I'm pretending that x is a constant. So all of that is a constant. Constants multiplied on will still be there, and then the derivative of y is 1, so it's just 4x. And then d squared z on dx dy. Technically that means that I started with the dy and I differentiate this with respect to x. And so that would mean I would get, let's see, the 4y is now a constant, and it'll be, so that'll be 4y. But just to make sure we get it right, we could take the x1 and differentiate with respect to y. Derivative of e to the x, there's no y's there, so that'll be 0. And the derivative of this would be 2 times 2y, which is 4y again. So you'll get the same answer either way. Okay? You only need one of them. Okay, so that's great. That's how to do second derivatives. And let's just think about what this means. The first derivative told you whether it was the bottom of a hill, bottom of a valley, or the top of a hill. It told you whether it was concave up or crap. The first derivative told you whether it was a turning point. The second derivative told you whether it was a local minimum or a local maximum. So what we want is, look, if it's a local minimum in the direction of the x direction and it's a local minimum in the y direction as well, then it will have to be a local minimum for the entire curved function. And so I need it to be a local minimum in both directions. And to be a local maximum, it should be a local maximum in both directions. But it's possible in 3D to be a local minimum this way and a local maximum that way. So for it to be going this way for x and this way for y, that's why it's called a saddle point. It looks like a saddle. And so your rule for the second derivative is to say, your rule for the second derivative is to say this. So you find the determinant of the matrix fxx, fxy, fyx, fyy, that determinant, which will be fxx, fyy, which will be that. So you get the ones, the double ones, and then the cross ones, and you subtract them, and you've got three options. They call this the discriminant. So you've got three options. Either it comes out to be negative, in which case it's called a saddle point, or it comes out to be positive, which has two options that go with it. You've got either one of the double ones is positive, then it will be a minimum. Or if either one of the double ones is negative, then it will be a maximum. You only have to check one of them, but they should both be positive or both be negative if they're going to be anything at all. And then the final rule is that if this is 0, then there's no conclusion. And they won't give that to you in exam. Feel free to come in. You have a Maths for IT, are you? Yeah, I'll be starting that soon, about 10 past. I'm still doing the one before. Okay, so as an example of how that works, so e.g. for z equals e to the x plus 2xy squared, and let's actually call it z equals f of x, y, so that we can use both. Find all the local maximum and minima. Now, I don't know if it's got any at all. I'm really sorry. It might not have any, so I'm just going to check first. So first, we need fx and fy to both be equal to 0. So fx was equal to e to the x plus 2y squared, and fy was equal to 4xy. So I need them both to be 0 at the same time. So my problem is that I need some way of combining these two equations together to figure out what x and y are. So, see, it's got two equations and two unknowns, but it's not that simple. So first what I'm going to do, actually I found it doesn't have any. That's really disappointing. Oh well. This doesn't have any, so I'll do a different example. This doesn't have any because I know that it's impossible for this to be 0 because I get that e to the x equals minus 2y squared. That would mean that e to the x is negative, and that's impossible. So e to the x is negative. That's no solution. So it's impossible for fx to be 0. It doesn't have any local maxima and minima. All right, let's do a different one. Let's try that one, hey? Hopefully this has one. Okay, so I need the first derivatives. Let's call it f, hey? So fx is 2x plus y cubed, because the y counts as a constant and the derivative of x is 1, and that's 0. Fy is, that doesn't involve y, so that'll be 0. The x will still be there because it's a constant multiplied. That's 3y squared plus 1. Okay. And I need both of them to be 0 at the same time. So oops, sorry. 2x plus y cubed equals 0 and 3xy squared plus 1 to be equal to 0. Yikes. Okay, so I need to somehow solve them. One method would be, if one of them didn't involve x, I could just solve it to figure out what y was and then sub that into the other one. And the other method that I'm going to have to use here is to rearrange one of them to get x equals and sub it into the other one. So I'm going to get 2x equals minus y cubed, x equals minus a half of y cubed, and then I can sub that into the other one. So I've got 3x y squared plus 1 equals 0, so I've got 3 times minus a half of y cubed times y squared plus 1 equals 0. So I've got minus 3 on 2, y to the 5 plus 1 equals 0. So if I put this over there, I'll get 1 equals 3 on 2, y to the 5. So I get 2/3 equals y to the 5, and so y is whatever the 5th root of 2 on 3 is. 2/3 to the 5th power, to the 1/5. Yay! And then I can sub that back in somewhere to figure out what x is. Sub into, what have we got? Sub it into x equals minus a half of y cubed which is totally awful, I'm sorry. In an exam, they'd give you something nicer. It'd come out to nice whole numbers or simple fractions. And so I get that my local max or minimum or saddle point occurs at minus a half of 2/3 to the 3/5 and 2/3 to the 1/5. That's the point that it happens at. It's above that point, right? That's the point down here on the xy, and it's above that. And then I would need to find the second derivative and sub those in, and this is where I'd probably figure it out in terms of decimals and sub it in so that I could be sure. But let's have a look at what it says. fxx, I should take my original fx, which was 2x plus y cubed. So I differentiate with respect to x, I get 2, because that goes to 0, I can just differentiate that. Fyy, the 1 will go away, 3x is a constant, So that's 6xy. fxy, I can take the fx and differentiate it with respect to y, so I'll get 3y squared. And that will be the same as fyx. And so now I need to figure out what they are at that point. So at whatever the name of the point was, at that point, I get that fxx is still 2, fyy is 6 times x times y, which is awful, but there you go. So 6 divided by 2 is 3. Add the powers, that's 4/5. And fxy is 3 times y squared. Which is 3 times. So when you do powers of powers, you multiply them, so that'll be to the 2/5. And so what do we get? We get my discriminant is fxx, fxy, fyx, fyy, which is 3 times 2/3 to the 2/5, 3 times 2/3 to the 2/5, and minus 3 times 2/3 to the 4/5. And even without calculating that, we can guess it's negative, because that times that is negative, minus that times that, and that's still negative, and so it's a negative, and so it's a saddle point. So, but just to be clear, we've got minus 6 lots of 2/3 to the 4/5, that's those two, minus 9 lots of 2/3 to the 4/5. That's 3 times 3 is 9, 2/3 to 2/5, yeah. And that's negative. So it's a saddle point. Right. Sorry for the complicated example. Didn't mean to, but that's what happens when you make it up. Which is what happens when you just take requests, right? You have to make it up. The only other thing that's in AQMF that it's actually not actually in Maths 1B is the Lagrange multipliers. And I'll just run through as short an example as I can think of. Hopefully I'll pick one from the lecture notes. I'm just going to organise these notes. Right. Okay, so there is this other thing that we might do. So we've got our surface, looks like whatever it is, and it might be that it doesn't even have a local maximum or minimum anywhere, but it might be that I don't care what the maximum is everywhere. What if I only wanted to know what the maximum was? What if I had this curve here, right? And I only wanted to know what the maximum was above that curve. And then it would be sort of here. So I only want to know what the maximum is above a certain curve that's down here. So I go up for each of those, and I get something that's around that curve, and I only need to know what the maximum is on that curve. That's what Lagrange multipliers are for, pictorially. But in essence, it's really about what the most important thing is in almost all situations that you use this for, is that your 3D function, your function of two variables, actually only matters on a certain curve, a certain constraint. So in economics, it's a budget constraint, where you know that your amounts that you spend and the amounts that you have, amounts that you spend it on, all have to add up to your budget. And so you have some formula that says whether which is about the goodness of various results. You want to, the classic in the microeconomics 2 textbook is apples and bananas, and you've got, well, I've got apples and I've got bananas, and I have some measure of how good I think apples and bananas are, and that measure of goodness is my Z. And so I say, well, based on my budget, what's the maximum goodness I can get? And I call that utility. So so what Lagrange did is that he was, I presume it was Lagrange that invented this process, is that he was extremely clever and thought of a way of doing this by just doing more partial derivatives. So I'm just going to get an example from the notes. Find the maximum of fxy, which is x squared plus y squared, subject to x plus y equals 1. Okay? So the concept is you have x squared plus y squared, which is some sort of shape, and it doesn't have a maximum. It has a minimum. It doesn't have a maximum. It goes up forever. This is AQMF. If you've come in for maths for IT, I'm just running over time from the previous one. This is Applications of Quantitative Methods in Finance. So you don't do this in Maths 1B. Yeah. X squared plus y squared doesn't have a maximum if you look at everything, but it will have a maximum subject to this. Okay? Hopefully. No, sorry, minimum. Minimum. It will have a minimum subject to this. It does actually have a minimum, but some of them don't have one at all. Okay. So what we'll do is we will create a brand new function that involves a new variable which is called lambda for Lagrange, I suppose. Lambda is a Greek L. So we'll create this new function. It will be your original function, and you will apparently add lambda times this arranged so it comes out to be equal to 0. So you chuck everything on the left-hand side so that it's equal to 0. And then what you'll do is you'll differentiate that with respect to x and y and lambda. You've created this new variable that you've added to help you solve the problem. So the derivative of this with respect to x is 2x. The derivative of this with respect to x is 0 because it doesn't involve any x's. Lambda's, in this case, constant, so anything multiplied by lambda, the lambda will still be there. And the derivative of this with respect to x is 1. And the y is 0, and that's 0 as well. So what we get is 2x plus lambda. And df on dy, so the derivative of that with respect to y is 0. The derivative of that with respect to y is 2y. Lambda is multiplied onto this bit, so it will stay there after I've finished. The derivative of that with respect to y is 0, 1. So I get 2y plus lambda. And the df on d lambda, that doesn't involve lambda, that doesn't involve lambda. Lambda is the variable now, and this is the constant multiplied it, so it might as well just be 11 lambda. So I'll just divide by, I'll just be left with the constant. Okay, so you'll notice that this is the original constraint again. And your aim is to make all three of them equal to 0 simultaneously. This one being 0 is your constraint. And so it's just like the other one. Normally when you're finding maximums and minimums, you need the derivatives to be 0. We've just got 3 to be 0 now. Sorry for everyone else for going over, but I can go over later for you guys too. So I need all 3 to be 0. So from the ones that involve lambda, I figure out a formula for how y is related to x. So I take from the ones with lambda, find a formula relating x and y. Okay? So I've got that 2x plus lambda equals 0 and 2y plus lambda equals 0. I've got a couple of options for what I could do in this case, because sometimes it ends up that there's actually an x and a y attached to the lambda. In this case, it's probably simpler to just rearrange it to get lambda equals. But what some people do is they put all the lambdas on one side and everything else on the other, and they divide them. There's lots of different ways of coping with this. I would just subtract them to make the lambda go away. So whatever you can do to make the lambda go away legitimately is a perfectly good approach. So there's a couple of options. I could subtract the equations. So 2x minus 2y equals 0, because the lambda minus lambda equals that. And that would give me 2x equals 2y, which would be x equals y. Or, alternatively, I could do this. And I could set them equals. Because 2x is equal to minus lambda and 2y is equal to minus lambda as well. So I get x equals y. Or the final option, which would be something that people do commonly, I could go 2x equals minus lambda, 2y equals minus lambda, and divide. And so I get 2x divided by 2y is, and lambda, minus lambda divided by lambda is 1. So they cancel, and I can times both sides by y, I get x equals y. They're your three options for what you could do. And depending on how crazy these formulas are, you might want to choose one over the other. But in case you've seen them, I just wanted you to see that they're all okay. Any one that you choose might be okay. And then once you've got that, you want to sub this into the third equation. So now we have x equals y and x plus y minus 1 equals 0. So since x equals y, well, since y is equal to x, I can replace everything with x. So x equals a half. And so do that. And then I can sub it into either one of these. Sub into x equals y, so we get y as a half as well. So the maximum occurs, the minimum occurs at, if it is a minimum, at a half. And it is, the minimum actually is going to be f equals x squared plus y squared, because that's the original function, which comes out to a half, coincidentally. And that's Lagrange multipliers. Sometimes be aware that this stage here, this bit with the lambdas, can be a little harder if there's x's and y's attached to the lambdas. That can make it a bit tricky. And that's why a lot of people use this divide version of the problem. If you can make it so that there's no pluses or minuses anywhere, no pluses between things or minuses between things, so you've just got blob all multiplied equals blob all multiplied, and divide, the lambdas will go away and everything will be left and you can deal with that. Cool. So I'm sorry I have to end there. Yep. Well, thanks guys, and good luck on your exam. There's still a few days to go.